In this setup, we have a simple pulley system with two masses. The lighter mass m1, shown in red, moves upwards, while the heavier mass m2, shown in green, moves downwards. As the system moves, the pulley rotates clockwise due to the tension forces in the rope. To analyze this system, we begin by drawing free body diagrams for both masses. For m1, the upward force is due to the tension in the rope while gravity pulls it downwards. We then apply Newton's second law to the mass m1. Using the equation F is equal to ma, we have T1 minus m1g is equal to m1 times a1. We always apply Newton's law in the direction of positive motion. Since the mass m1 is moving upwards, we take that direction to be positive. Now we analyze the pulley, which rotates clockwise due to the difference in tensions on each side. The torques generated by the tensions T2 and T1 create the rotational motion. The equation of motion is T2 times R minus T1 times R is equal to I alpha, where I is a moment of inertia and alpha is angular acceleration. It is important to note that the weight of the pulley and the reaction force do not contribute to the rotational motion because they both pass through the center of the pulley, and therefore we can ignore them when writing the equation of rotation. Finally, we apply Newton's second law to the mass m2, the heavier mass, which is moving downwards. We take the downward direction to be the positive direction, and applying F is equal to ma gives us m2g minus t2 is equal to m2 times a2. We then consider the kinematic relationships between the two masses. When the mass m1 moves upwards by a distance d1, the mass m2 moves downwards by the same amount d2. So we get d1 is equal to d2. When we take the derivative of d1, we get d1 prime is equal to d2 prime, which means the velocity of mass m1 is equal to the velocity of mass m2. Taking the second derivative then gives us the acceleration a1 is equal to the acceleration a2. We can also notice that when the pulley rotates by an angle theta, the amount of rope wrapped around the pulley is r theta. This is shown in yellow. And this should equal the amount of rope that moves upwards. Therefore, the distance d1 is equal to r theta. When we take the first derivative, we get d1 prime is equal to r theta prime, and the second derivative gives us d1 double prime is equal to r theta double prime, which means the acceleration a1 is equal to r alpha. We now have 5 equations and 5 unknowns. At this point, the mechanics is over. We have to simply use mathematics in order to simplify this system of equations to find the unknown variables. We can first substitute a2 as a1 because a1 is equal to a2. We then rewrite t1 and t2 and substitute them in the third equation. In the next step, we have to substitute that alpha is equal to a1 over r. Now the only unknown variable remaining in the equation is a1, and we can solve this to find the acceleration of the mass m1.